But it's a privilege for me to be here and to celebrate with you the 30th anniversary of VJT. Vijay Alreja and his family have become dear friends of ours, and so it's a real honor for me to be here. So, Vijay, we have a little gift for you. Where's the slides coming up? So, 1987. This is a Côte Rôtie from Gigal. It is actually at home. I didn't bring it because I didn't come from home, but I was able to secure this about 3 weeks ago, and it's very, very special. Even if you had the money, you couldn't buy it. So, so hopefully you will enjoy that, and but more importantly, hopefully you, probably not me, but you and your Sonia, Rahul, Mita, and Arya, and Shweta will drink to 2047, because I understand it's going to be a fabulous year in 2047. I've just been told, I have a 40-minute lecture, but I've just been told I got to do it in 20 minutes, so I'm going to skip a few things. But what I really want to do is really leave behind, it's not a technical talk about CT or X-ray, so in that way, hopefully it will be edu entertainment for some of you. But why green and why sustainable development is, in my opinion, and many others as well, is one of the grandest challenges of the 21st century. And just a few examples of what we're doing, and I'm going to focus on only two things. It's one is metals recovery, recycling you want to call it, and the other one is machine learning. But the previous speakers have done such a wonderful job on that, I'm only going to spend maybe 1 or 2 slides on that. Why green? Well, I think many of you know this, but we have really populated this planet of ours. And all you got to do is just remember one thing, if nothing else, is that in 100 years, the last century, the 20th century, we entered it with 1.6 billion people, and we're exited that century with 6.1 billion people, and that number is going to be about 9.2 billion or something in another 20, 30 years. So obviously people consume, we all do, and with what's happened particularly in the history of the world in the last 30 years, where the quality of life, which is a good thing, has gone up around the world. If you see what has happened in rural parts of China over the last 20 years, parts of India, and many other parts of the world, there has been profound changes that have occurred, which have impact. And that impact is that we're consuming more and more. So just look at metal production trends. And the indices or the metrics are different for each one. Obviously, steel is going to be different than diamonds. But what you will see in this slide is that over a period of time, we are using more and more materials. Now, I don't expect that every one of you here is a mineral engineer or know exactly what the processes are. Some of you do, who I know are materials people in the audience. But these things come from ores from the ground. We extract the ores from the ground. All these metals that you use are oxides in the earth. Aluminum is aluminum oxide. Iron is iron oxide, whether it's hematite or pyrite, but it's an oxide. And what we got to do is break those bonds using a lot of energy, and sometimes a lot of energy, so we can make the metal and use it. So the ores where these metals come from the earth, and the ore grade means that you've got to dig a lot more ore out of the earth to be able to get the metal. So the ore grade is going down. So whenever you have two things going in opposite directions, and Jeff can tell you about it, it's not a good thing. We're using more and the grade of the ore is going down, so we really have an issue. And just to personalize this with some examples, the computer chip has been around a while. Every one of us uses it. Back in the 1980s, the chip had about 11 elements. 1990s, a couple of more elements, maybe 15. More recently, these are slides from Intel, 2004 45 elements, and right now it's about 54 elements, I think. In your cell phone, these are all the elements that are used. So the things that we're making out of materials are not what our parents and grandparents really thought about, more structural, making sure the bridge is not going to fall apart. But we're more interested in taking your iPhone and putting your fingers on it and things get bigger or smaller, functional. And the elements of the periodic table are, not all of them are critical, but there's certainly a finite amount of them on the Earth. So these elements, are we recovering them? Are we recycling them? So UNEP, United Nations did a study. I used the wrong slide there. That's a 2010. They did another one in 2012. But actually, interestingly, it's almost the same data. It hasn't changed. What you see there is end-of-life recycling rates. So if you take the lanthanides, for example, which are these elements here, like terbium, europium, neodymium, cerium, et cetera, the recycling rate is less than 1%. If you look at all these numbers, there's nothing higher than 50%. So we're not really recovering all these materials, and with the consumption rates and the numbers that you saw earlier, it's an issue. It's an issue. So sustainable development really is something that we're facing in the 21st century. Our civilizations have been coined or described by materials, whether it's the Stone Age or the Bronze Age or the Iron Age, and now, we may as well be the everything age. So it's an issue that we have to deal with. So sustainable development for the 21st century with all of the context that I have provided here is probably one of our grandest challenges. And if you just boil it down to the basic human needs, and this doesn't have cybersecurity in it, doesn't have a lot of other things, but these are just basic Maslow's hierarchy of needs of society, if you will. You need energy, you need food, you need water, shelter, housing. Mobility is really transportation in a variety of methods. It's not only cars and airplanes, bicycles, motorcycles, but it's also Wi-Fi, et cetera. And health. So those are basic needs of our 21st century humans on the planet. But there's one thing that's common to all of these, and that's materials. I'm going to make the time here. So for each one of these silos, materials is a crosscut. And the other thing that might surprise you is the social sciences. I think for the 21st century, the social sciences is the physics of the 20th century. The human dimension, understanding cultures, understanding all of the variety of social issues, as well as materials are the crosscut, enabling solutions to some of the challenges that we face. So it's not just innovation and technology that's going to do it. Education is a key point. There are three legs to the stool. The other one is policy. Policy not only at the governmental level, but at the universal level. The World Economic Forum right now is actually debating this, whether do we have policies for materials for the world. Just take this thought with you. I'm not going to try to answer it. If you're a company and you're digging things out of the earth, the ore, making a material, and selling the goods, manufactured goods to someone or to consumers, who owns the ore? Is it really yours? Who owns that material that's in the earth? Does it belong to our grandchildren or to the children of our grandchildren? Whose responsibility is it that after we use that material, we'll put it back in the earth so that 300 years from now, somebody else is going to be able to use it? So these are major philosophical questions that really cannot just be solved by education, being aware, and cognizant, and technology. There's some policy issues. I'll give you one example of why policy is so important. What you're going to be looking there at that, let's first understand what we're looking at. That's about 6 years old data, but it's still very relevant from EPA. And what you have here on the ordinate is recycling percentage rate. And over here are a variety of different products. PET bottles are actually fairly low. Glass is low. Aluminum cans, you think it's high. It's about actually 51% this year. It's gone up a little bit. These are US. In Europe, it's higher. But look at in the US, North America, auto batteries is 96.2% recycling rate. That's pretty cool. Why is that so? One, there's a business model. Sonny and I were talking about it right before lunch. There's a business model. It's sustainable. It works. Economically, it's doable. There's a collection system. There is an EPA regulation that says lead is bad. So, you know, policy does work as long as it's done across the board for everybody. So the need for recovery and reuse is really not an option. It's something that has to be done. I may just want to skip this because of the time, but material scientists, there's colleagues of mine here, Dr. Aziz Asfahani, who just got inducted to the National Academy this weekend, is here with us. He's the CEO of Questec Corporation. That's what they do. They design materials so that they perform better, and they know how to deal with the whole architecture of how to put the materials together as a design process. And as I said, I'm going to skip it, but essentially you can remember, you know, you have the performance that dictates what you want, how you're going to make it out of what the composition is, what the structure is going to be, how you're going to process it together so it has certain properties. But I'll just skip the animation. So material design is a process where you develop new materials, you select the materials, you optimize the performance. But what's missing in here? What's missing is that we do not make right now, very few examples, but not as a whole. We don't design and manufacture things for disassembly. Think about it. Your iPhone or your whatever it is, Samsung or whatever, if you want to recycle that, the first thing you want to be able to do is take the battery out so that it doesn't explode. You can do so if you go on eBay and buy a special screwdriver. So the corporations are making things that can be easily repaired. They're much more willing to just trash it. We'll send you a new one. It's much easier. And I have a whole bunch of personal experiences with that as well. A good example for some of the people in the room who have gray hair or no hair, go to a classroom at the university, the freshman class, and ask them what a cobbler is. Somebody who, you know, resoles the shoes. They have no clue what a cobbler is. In fact, the whole idea that you can actually take a shoe back to someplace and repair it so that you can reuse it is a strange idea. So having the end of life in mind at the onset of the manufacturing process, I think, is a key paradigm that will be one of the enabling solutions for sustainable development in the 21st century. So we need to reduce the waste, or think of waste as a resource, and recover it and reuse it. And of course, you have waste that you create when you're making materials, and you have waste that you create when you use it as a consumer, post-consumer waste. So just two examples, so it's not abstract. Aluminum. Aluminum is made from bauxite. I'm not going to go through all the details, but as I told you, it's a very covalently bonded, it's a very strong oxide, and you got to break those bonds, the Al2O3, and you got to put a lot of energy into it. So for every pound of aluminum you make, you put a lot of energy into it. But more importantly, that's not written here, for every pound of aluminum that is produced, for every pound or every kilogram, you also produce 3 kilograms or 3 pounds of red mud. So for 1 pound of aluminum, you're producing this as a production waste. What happens to it? It usually ends up in landfills like that or sits like that. There's a lot of valuable materials in there, like scandium, lanthanides, and we have major programs in this area to recover these materials and reuse them with a sustainable business model. The other one is post-consumer waste. You know, I think I told you about ores and metals, et cetera, earlier. To get 3.5 grams of gold, to think about the ring you have on your hand or jewelry, to have 3.5 grams of gold, you got to dig 1 ton of gold ore out of the earth, 1 ton. Today in landmines, urban mining, if I have 1 ton of used cell phones, I can get 200 grams of gold, and I can get 2.5 kilograms of silver. Okay, so the urban mining, the landfills that we have today are really a resource for recovering these materials. So the takeaway message here is reduce production waste, and I could give a half-hour lecture on each one of these, but I don't have the time. Reduce post-consumer waste, design and manufacture for disassembly, and create value from waste. And our great-grandparents, and we have quite a few people from Germany here, right? Raise your hand. How many people are here from Germany? Yeah, quite a few. At least 9% of the audience. Well, they figured this thing out a long time ago. That they had a strategy to recover and reuse, and it was this thing. Now think about it. If you were working for a food manufacturing company, would you go to work and say, okay, I got a new product in mind, boss. We're going to take all the leftover meat. We're going to chop it all up. And what are you going to do? Well, we're going to put it in the casing. What's the casing? It's the intestine of the animal. We're going to make it into a little link, and we're going to sell it. Yeah, good luck. But they didn't waste anything. They reused everything. I'm sorry for some of you who are vegetarian. I just thought of it now. But the whole idea is recover and reuse. It's a great example, you know. So you look at, you benchmark. What are the systems that have been sustainable year after year after year? Nature. Nature is a great example of a natural system that's been around a long time. I remember Pittsburgh when I was a young man, you know, steel mills everywhere. You couldn't wear a white shirt. In the old days, it would get dirty. I'm looking at Jeff because he went to Carnegie Mellon. Beautiful city today. The rivers are clean. Allegheny is clean. G plant in Cleveland, the Cuyahoga River was on fire. Today, it's beautiful. So nature sort of remedies itself. So what can we learn from the natural ecosystem and apply to the industrial ecosystem? Well, it's a closed loop system. Our industrial system is open loop, it's linear. There are a lot of subsystems in the natural ecosystem, whereas that doesn't really exist in the industrial system. It does sometimes, but it's few and far in between. As I said, it's cycling, whereas it's linear in the industrial system. The other odd part is that nature used very few elements, including our bodies. You know, we're using most of the periodic table. And the indicator of well-being in nature is equilibrium. It's not growth. Imagine Jeffrey Immelt putting in his annual report, we haven't really grown in the last 5 years with equilibrium. Yeah, that's not going to happen. So, you know, we really need a cradle-to-cradle approach. There's a lot of work that's been done by the Ellen MacArthur Foundation on circular economy rather than a linear economy. And a lot of subsystems come into being, and actually there's a good business model to make it sustainable. This past June, I had the privilege of going to Armenia to set up one of our project centers, and I was at this monastery from the 13th century, and everywhere was these circles. So I asked the guy, what is this all about? He says, well, that's always been around in all the monasteries. There's one from 500 AD, you can go take a look, that life is circular, that we're born on earth and become part of the earth. In fact, in the Armenian church, cremation is not allowed. You know, you got to go back to the earth. So the circular economy concept is not such an odd thing. It's been around a long time, right? All right. To do that, you need new business models, new paradigms, performance contracts, perhaps. Products become services. You know, you don't buy a car anymore. The guy who makes the car is responsible for it. You just use it as a service and return it back. We can spend more time on this, but there's a whole bunch of things that need to be put in by policy, by regulation, by standardization, and you need a regenerative system. The collection system has to be put in place. A good example is the lead-acid batteries. Okay, what are we doing in this space? How much more time do I have? 5. Boy, this is going to be a quick 5 minutes. The Metal Processing Institute, most of the time it's metal processing. There are a few days of the week that I think it's a mental processing institute, but you know, overall it's a wonderful institute. I'm the founder of it. My dearest friend and colleague, Brajendra Mishra, is now the director, doing a great job. We have several centers in metal casting and thermal processing, recovery and recycling, and we have a new center that we just launched on data. Machine learning is a key feature in it, but processing data. And we also have, and I'm happy to see Professor Wang here from Shanghai Jiaotong. We also have a branch in Shanghai Jiaotong University. But essentially, it's a collaborative consortia with several centers where we develop knowledge and develop people, essentially. The Recycling Center is of interest to you. It's a National Science Foundation Center with colleagues in Colorado School of Mines, where they bring a lot of extractive metallurgy experience. At KU Leuven in precious metals, and University of Tokyo, who really has a completely different ecosystem about green engineering than we do here in the Western world. So together, we're working on a variety of different projects. There's one more, I think, on the on scrap characterization, reuse opportunities, all kinds of projects. The ones that will be of interest to you, I think, for the people in the crowd here, is this one here, scrap characterization. But every one of these projects, every one of them has an opportunity for, including the LIBS one, the laser-induced spectroscopy, for NDT and the kinds of technologies that you do here. Also working quite a bit on lithium-ion batteries in terms of how to make them and how to recycle them. So in a nutshell, very quickly, we're doing quite a bit in this area. 4 university partners. We have professional partnerships, 17 members. We've launched a Journal of Sustainable Metallurgy. We have formed 2 companies that are doing startups, so they're doing very well. Current projects 10, and quite a bit of funding that has allowed us to do that. So it's a good success story. But 2 specific foci before I leave are materials recovery, particularly aluminum and titanium and things of that sort, and machine learning. So because of the time limitation, let me go very quickly on materials recovery. Take your average car today that you use. Whether it's a European car or a US car, doesn't matter. But in the US numbers, we have about 253 million passenger vehicles that are in use today, of which about the average weight is about 1,500 kilograms. And of that number, about 7 to 8% is made out of aluminum. So there's quite a bit of aluminum that's being used in the car. This wasn't the case 20 years ago. There was a lot more steel in it. So to put it down in rough numbers, about 27 million tons of aluminum is in use today. So what's going to happen at the end of life of these things? Well, today what happens, I'm calling that downcycling. I'm going to show you what upcycling means in a minute. At the end of life, it gets dismantled. Some of the stuff is resold, retail parts, flattened, auto hull goes into the shredder, and there's magnetic separation that occurs, eddy current separation. If you haven't ever seen one of these operations, it's quite fascinating. Actually, cars are going into a big shredder, just like your Cuisinart where you're blending things, you know, to make your smoothie. Big cars that are flattened are going into this machine, and they get shredded. And when they get shredded, it gets separated into 2 things, ferrous and non-ferrous. The ferrous part, I'll show you later, goes to the steel mills, gets remelted, and steel is made. The non-ferrous part gets further separated. I didn't make up these names, but it was done during the war, 2 telegraphic codes, whatever. It's either Zurich or Zorba. The Zorba contains twitch and zebra. You know why I told you I didn't make up these names. Twitch and zebra, and this twitch includes Zorba and twitch. This is the material that's 98% aluminum, which is the scrap. But there are 350 alloys of aluminum. So it's all mixed. We have no idea what's in it. So it gets sold as scrap, so not much value, mostly to China. Whereas if we could take that scrap and separate it by clever or intelligent sortation, there would be value in it. We just remelt it and reuse it. So the opportunities are optoelectronic sensing, XRT, XRF libs, as well as in the twitch. So as I said, most of it is exported. 90% of it is exported at a very cheap value. All the energy you put into that aluminum is gone, and the upcycling opportunity is wasted. This is the ferrous scrap that goes to the steel mills. So a lot of aluminum is going to be used. I'll skip this, but what you want to do is upcycle. Upcycle means create value. So you take all your scrap, very schematic, with a sensor, identify what it is, and then reuse it by just remelting it. It could be an X-ray transmission. We're working closely with Steinert in Cologne, Germany. I don't have to explain to you what X-ray transmission is in this group. It could be XRF, or it could be LIBS technology. But essentially what we're doing now, and this is called the mini mill, aluminum mini mill, which is so exciting. You take the scrap that is all mixed up, you have no idea what's in it, there's no value really, but we chemically sort it, not by visual inspection, by identifying what the chemistry is, cleaning it up through a certain process, remelting it, you taste the soup, see if it tastes good, if not, you add a little whatever it is that you need to add through LIBS technology, and then the final product. Plant would look something like this. We have a big ARPA-E contract with a bunch of partners, and it's our 4th year. But essentially, it's a fascinating process where a lot of sortation technology is used. Lastly, a lot was heard this morning by 2 wonderful presentations by our colleagues this morning. But machine learning and material science is one of the new emerging areas that we're really hopefully leading it, but let others judge it. One example, foundries. $32 billion a year industry in the US. They got lots of data in the melt shop. They got lots of data from CAD. They got lots of data and information, not even information, data from the process in the plant, die casting plant, shot temperature, cycle, the speed, all kinds of data. Then they have data from customer scrap return, and they have data from NDT, but none of these things are fused together. There's no platform for it. So what we're doing is developing essentially a platform to enable the manufacturing plants to fuse data to enhance process control and create knowledge-based approach. So if you think of the cartoon, currently the gold mine is there, and you're over here, and that's a little poor guy over here. What we want to do is really create that bridge where essentially, as T.S. Eliot said, you take, you take the data to go to information, to wisdom, which will allow you to have competence and cognition for your processes. So I've gone over that very quickly. A lot more was presented this morning, but this is a very important area where I truly believe that CT scanning, X-rays, the kinds of things that all of you are making in this room are going to be very, very, they're pivotal, if not critical, to ensure that manufacturing advances through these enabling technologies. So with that, I want to thank you for your attention. I went through it fairly quickly, but hopefully some of it resonated with you, and I made at least 1/3 of you happy.